Welcome back, everybody. Finally, we're going to make another video here. It's been a little while. We're going to try to generalize Theorem 14.3.1 from this playlist into the following theorem. So we're going to use Raynaud's results that we've been talking about and Ramakrishna's theorem, which will be covered soon, to generalize actually just the good reduction parts of Theorem 14.3.1 from this chapter to the following theorem that we'll call 14.3.5. It says, let R be a complete local Noetherian ring with finite residue field K of characteristic P not equal to 2. Choose a flat representation rho bar from the Galois group at P to GL2 of K, such that the determinant of the residual representation is cyclotomic when restricted to inertia at P. And then choose a continuous lift rho from GP to GL2 of R, giving rise to an element of the flat deformation problem D flat sub rho of R, which will be defined next section, although we've sort of already defined this in previous chapters. Let's let phi sub 2 from IP to F cross P squared to GL2 of FP to GL2 of K be the map arising from a choice of FP basis of FP squared. Psi 2 here is the second fundamental character. Then, 1, if rho bar is reducible, there exist continuous unramified characters chi sub I bar from GP to K star, such that rho bar is equivalent to omega chi 1 bar star 0 chi 2 bar. Otherwise, rho bar is absolutely irreducible, and rho bar restricted to inertia at P is isomorphic to phi sub 2, that composition above. And so, rho bar restricted to IP tensored up to FP bar is isomorphic to psi 2 direct sum psi 2 to the P power. 2, if rho bar is reducible, there exist unique continuous unramified characters chi I from GP to R cross, such that rho is equivalent to epsilon chi 1 star 0 chi 2. So here epsilon is the p-adic cyclotomic character, omega is the mod p cyclotomic character. From this, you can see in particular that when you restrict at rho to inertia at P, you just get epsilon restricted to inertia at P, and chi sub I mod the maximal ideal of R is chi sub I bar. Okay, so these two results here kind of tie together. And then 3, kind of the hard one, is if rho bar is irreducible, then det rho restricted to IP is just automatically epsilon restricted to I sub P. Okay, so this should look familiar. We invoked this theorem actually in chapter 12. You can see theorem 12.5.1 in my playlist. We proved the first 2 parts of this already, actually, and we said we would delay the proof of the third part until later on. Well, now is later on. So we're going to prove the third part. Let's do that. We're going to have to invoke a result to be proven later in this chapter that we'll call Ramakrishna's theorem. You have to be a little bit careful here. The proof of Ramakrishna's theorem will not invoke this result, so there won't be any circular logic. We do encourage the reader to come back to this proof once Ramakrishna's theorem has been stated to make sure of this. Okay, so let's prove 3. So again, what is the statement? If kind of you have your flat representation here with cyclotomic determinant, then the determinant of rho restricted to IP, where rho is some like flat lift of rho bar, is just cyclotomic. Okay, let's set O equal to W of K, the ring of Witt vectors over K. Ramakrishna's theorem then says that there's a universal WK deformation ring R flat rho bar for that flat deformation problem. So in other words, the flat deformation problem is kind of representable. That's what Ramakrishna's theorem says. We will prove this later, and we'll also formally define everything involved next section. Okay, so we've got this WK deformation ring R flat sub rho bar associated to rho bar, and this is we actually know what this ring is. It's isomorphic to like a 2-variable power series ring over W of K. Okay. It suffices to show that the associated universal flat representation, so the universal deformation associated to this universal ring, has inertial determinant epsilon restricted to I sub P. Okay, because then kind of that cyclotomic determinant will descend all the way down to rho. A quick result of faulting says that we can actually extend K, our ground field, without loss of generality. You can see Weil's paper, pages 457 to 458. This is a pretty easy argument. So from now on, we're going to assume that K is actually large enough so that there exists a continuous unramified character chi from GP to K star, such that omega inverse det rho bar is chi squared. It is possible to find such a chi because GP mod IP isomorphic to Z hat has no non-trivial 2 torsion. So you have to be able to actually find this character chi here. Okay, by the theory of Galois descent, the flatness of a GP representation is unaffected by unramified twisting. You can see, for example, the discussion we had after Theorem 14.3.3 on Henselization for this. Okay, so twisting by the unramified Teichmuller lift of chi inverse gives, by Ionetta's lemma, an isomorphism between the universal flat deformation rings of rho bar and rho bar chi inverse. So they're kind of the same rings up to isomorphism. And so really what this allows me to do then is just reduce to the case where the determinant of rho bar is omega. Okay. We claim that up to isomorphism, there's actually only one continuous representation rho bar from GP to GL2 of K with determinant omega, which is isomorphic to phi2 on I sub P. This representation is self-dual. Okay, so this is kind of what we're after. And this representation is, as a matter of fact, defined over FP, not just some extension. First, let's check the uniqueness part of that claim over FP bar. Let's let L be the unique quadratic unramified extension of QP, and let G be the Galois group of L. Since Frobenius at L acts on tame inertia by P squared power because of the quadratic extension, okay, we see that rho bar of G commutes with rho bar of inertia at P. Okay, that's a quick little exercise for you. This means that rho bar of G is actually contained in the FP bar vector space generated by rho bar IP. Okay, in particular, rho bar of G is an abelian subgroup of GL2 of FP bar made up of diagonalizable matrices. What that means is that rho bar restricted to G is a sum of two characters. That's the only way that this can happen. And we can write these characters in the form alpha equals chi psi 2 and beta equals chi inverse psi 2 to the P, where chi is unramified, by the discussion above in this video. Okay. Now, these characters must be exchanged by the action of Frobenius at P. So chi of Frobenius at L equals chi inverse of Frobenius at L. And these have to be plus or minus 1. From what we've seen so far, rho bar of Frobenius at P has trace 0 and determinant 1. Go check that, please. So its square, rho bar Frobenius at big L, is negative of the identity. This tells me that chi of Frobenius at L is chi inverse of Frobenius at L, and this must be negative 1. Since we've now determined all traces for rho bar, uniqueness follows, right? So this is kind of a Brouwer-Nesbit thing, okay? To construct rho bar over FP, extend phi2 to a map from G to GL2 of FP, mapping Frobenius at L to negative I2, so the negative of the identity matrix. Then map Frobenius at P, kind of below that, to anything in the normalizer of phi2 of IP whose square is minus 1, i.e., just map it to something with determinant 1, which is not in phi2 of phi sub 2 of I of P. Okay, and this proves the claim. So we have uniqueness, okay, and existence. So we are all set. Now, applying part 1 of the theorem, which remember we already have from a previous video, and Falting's observation in reverse, we may reduce to the case where K is FP, so we can kind of shrink the field back down. That's what I mean by Falting's observation in reverse. And so really then we're just considering the case where R flat rho bar is ZP double bracket T1, T2. So now instead of looking at like W of K in two variables as a power series ring, we can just assume the coefficients are in ZP by shrinking back down. It's now enough to check that the universal flat deformation has an inertial determinant epsilon restricted to I sub P on ZP valued points. But a ZP valued point is just a P divisible group over ZP with P torsion representation rho bar. Okay. So now we've reduced to the following kind of simpler statement. It says the following: if rho from GP to GL2 of ZP is the generic fiber of a P divisible group gamma over ZP, such that rho mod P is isomorphic to rho bar, then the determinant of rho is cyclotomic when restricted to I sub P. This is now just like a much simpler statement to prove. And now we're going to invoke Raynaud's results. So by Raynaud's results, theorem 4.2.1 in Raynaud's main paper, it suffices to prove that dim of gamma is 1. So gamma is a one-dimensional P divisible group over ZP. Since rho bar is ramified, gamma is evidently not étal, and so that means the dimension of gamma is at least 1. On the other hand, the dual gamma star has generic fiber representation, what? Rho bar star. But remember, we have self-duality here, so that's just rho bar. Well, that means by the argument we just got done doing up here, dim of gamma star is at least 1. But if you look at like just Tate's P divisible groups, section 2.3, proposition 3, you see that dim gamma plus dim gamma star has to be the height of gamma, which is 2. Okay, but we know both of these are at least 1, and their sum is 2, so each one of them is 1. So dim gamma is 1, which is exactly what we're trying to prove. Okay, so that proves, minus quite a few technical details, I suppose, the full theorem, which generalizes theorem 14.3.1. We have a lot of information now about good reduction when it comes to flat representations. We just don't have Ramakrishna's theorem yet, so that's kind of a big thing. By the way, just as a remark, Ramakrishna's theorem does hold in the residually ramified and irreducible case even when P equals 2. which means part 3 that we just proved above is still true when p equals 2, but we're not going to prove this because we don't need it and it's harder, okay? So reality check, what do we have to do? Like, we've been like proving in quotes r equals t for like a few chapters now, and it's like we proved it over the course of 2 or 3 chapters. Then we kind of reduced the situation to a few holes we had to patch up, which is what this chapter is about. Those holes all having to do with the flat deformation functor. What do we have to do? If you think about it, there's really only 2 things we haven't done yet. We have to formally define the flat deformation functor carefully, and then prove Ramakrishna's theorem that it's representable, and we're all set. So we'll start doing this next video. Thank you for watching, and I will see you then.